Deepsea gigantism, a phenomenon of the abyss. Deepsea gigantism, also known as abyssal gigantism, in the abyssopelagic zone, which roughly starts 4,000 meters deep, is where gigantism occurs prevalently compared to the other pelagic zones. It is an evolutionary trend where deep-sea creatures grow to much larger sizes compared to their shallow water or surface-dwelling relatives. This phenomenon is observed across multiple taxa, including arthropods, a phylum, not the same as crustaceans, which are a subphylum of arthropods, because crustaceans have different body segmentation, i.e. three main parts: cephalothorax, abdomen, and uropods, as opposed to the head, thorax, abdomen in other arthropods. They have biramous legs, so legs that split into two branches instead of single branch limbs, and the list goes on with about 5 other things. Arthropods such as crabs and isopods, cephalopods such as squids, octopuses, and cnidarians such as jellyfish, and vertebrates such as sharks and fish all exhibit this phenomena. And to go deeper, we have to find the causes of deep gigantism. There are several theories that try to explain why organisms at extreme ocean depths tend to grow much larger. The first hypothesis is the cold temperature hypothesis. Cold environments often slow metabolism and prolong growth periods, allowing organisms to grow larger before reaching reproductive maturity. Imagine finding a foot-long pill bug crawling along the ocean floor. That's the giant isopod, a deep sea cousin of the tiny roly-polies in your backyard, except 50 times bigger. The second theory is low predation pressure. Fewer predators in the deep sea allow organisms to grow bigger without being eaten in early life. With fewer predators, creatures like the colossal squid can reach lengths up to 46 feet, 14 meters. That's as long as a school bus, and that's not even the scary part. It has rotating hooks on its tentacles and dinner plate-like eyes. The third hypothesis is the high pressure effects. Increased hydrostatic pressure at these extreme depths can favour large body sizes for structural integrity and physiological efficiency. Deep-sea creatures sometimes go months without eating. When the food finally appears, they outcompete each other. Enter the giant amphipod, a shrimp-like scavenger that can grow to the size of a loaf of bread instead of a few millimeters. And the fourth hypothesis is food scarcity adaptation. Larger body sizes may provide energy storage advantage, allowing these creatures to survive long periods between meals. And the final theory is oxygen availability theory. The larger body sizes may be an adaptation to the deep sea oxygen limitations, with the bigger animals having more efficient oxygen storage and utilization mechanisms. Now I'm just looking at the enigmatic deep sea giants. What is the examples? What are we talking about here? Well, the giant phantom jelly and the Deepsea enigmatica are some of the best examples and some of the most interesting examples that I think of. Among the many enormous deep sea dwellers, some of the most mysterious are these two. The giant phantom jelly, one of the rarest and largest deep sea jellyfish, first described in 1910. Sightings are scarce due to their extreme habitat, with fewer than 130 observations. Typically found at depths of 1,000 to 6,600 feet or 300 to 2,000 meters deep. Can reach estimated 10 feet in diameters or 3 meters, with ribbon-like oral arms extending over 30 feet, 10 meters. Unusual features: no tentacles. Unlike most jellyfish for capturing prey, the giant phantom jelly relies on its 4 long, flowing oral arms, which act likely as a function of as a drifting net to ensnare prey. Is it a deep-sea predator or filter feeder? Scientists are uncertain whether this species is as active as predator or passively collecting plankton. Extreme adaptation, its gelatinous bell-shaped body allows it to conserve energy whilst floating in the deep currents possibly even mimicking other organisms to avoid detection. The most known footage of this comes from remotely operated vehicles, ROVs, in deep sea and deep sea submersibles operated by ocean research groups such as MBARI. The second of these is Deepsea Enigmatica. It was named after the deep sea submersible Deepsea 4000, which first observed in 1996. It's found at depths of 2,000 to 5,000 feet, 600 to 1,500 meters. It has a very eerily thin, translucent and membranous bell, which represents a floating, shape-shifting plastic sheet, and grow up to 2 meters, 6.6 feet across. Again, it has unusual features: no tentacles. Instead of trailing tentacles, it has an intricate net-like structure within its body. It has a very mysterious feeding mechanisms. Unlike most jellies, Deepsea doesn't actively sting prey. It may function like a drifting parachute trap, enveloping small organisms that unknowingly drift into its bell. Shape-shifting behavior. Deepsea can change shape dramatically, sometimes pulsating. It has a strange internal network. Unique hexagonal mesh of canals line the interior of its bell, possibly aiding in nutrient distribution or some sort of structural support. Sometimes this creature is confused with Deepsea reticulum, shares many similar characteristics, but has a more defined reticular net-like structure. Why are these creatures so elusive? Extreme depths. Both Medusa gigantica, the giant phantom jelly, and Deepsea enigmatica live at depths that are rarely even explored. We've even explored more of Mars than mapping our own oceans. There are very low encounter rates. Unlike fish or cephalopods that move actively, these jellies drift passively, making them harder to track, and more so even with other dormant, slow-moving creatures. There are limited research missions. Deep sea exploration requires expensive ROVs and submersibles, limiting opportunities for studying it. And with this, the question still lies: how much more will we know about the deep sea? How much more is to uncover? This is the Enigma, and here I'll see you guys in the next video.